The design of experiment, DOE, as a statistical method has been widely applied in different fields of science and industry, especially to support the design, development, and optimization of products and processes. Although DOE was developed primarily for agricultural purposes by British statistician Sir Ronald Fisher in the 1920s. Currently, the DOE methodology is an effective tool for upgrading the level of measurement and assessment in many different areas of research. The design of experiments includes a series of applied statistics tools used to systematically classify and quantify cause and effect relations between variables and outputs in the studied process or phenomenon, which may result in finding the settings and conditions under which the process becomes optimized. Well-established, general guidelines and procedures are available to support the implementation of DOE methods. These steps include defining the objectives and response variables, determining factors, levels, experimental design type, and experiment execution. Variables in the DOE, such as the number of factors, levels, and the logic to select them, usually depend on the type of investigation, screening, characterization, or optimization, the process type, and the available resources. However, there is a multitude of different DOEs that can theoretically match the type of investigation, and therefore, it is not straightforward to identify which design provides the best possible insight using the least resources. In general terms, a good experimental design ensures the validity of the given insight. However, good and excellent DOEs differ in efficiency, that is, the ratio between extracted information from the examined process and the invested resources. Overview of the main DOEs. Each DOE can be seen as being composed of a series of steps: the planning, the execution of the experiment, and the analysis of the collected experimental data using various statistical methods to draw valid and objective conclusions. Each DOE starts with selecting the system or process and recognizing the investigation problem. The problem statement leads to establishing the objectives based on which the performance indicator, response variable, needs to be defined. The response variable should represent a quantitative measure of system behavior. As an essential step in the whole process, the factors affecting the performance indicator and how they are discretized, the number of experimental runs, and a suitable array need to be defined in the second stage. The third stage covers the performance of the experiment according to the designed array and the collection of data. The last step includes data analysis using statistical tools, ANOVA and associated statistical methods, and interpretation of results, leading to a better understanding of system behavior or its optimization. To examine the impact of several factors and interactions among them on the response quantity, experiments need to be performed systematically using factorial experiments, so-called factorial experimental designs, where several factors are altered during each experimental run. A factorial experiment whose design consists of all possible combinations of the chosen factors and levels is called a full factorial design, FFD. Effects of all factors, main effects, and interactions among them are considered in this design, making it a potent tool that, compared to other experimental designs, provides the most comprehensive insight into the system's behavior. If all factors K have the same number of levels, N, the total number of runs is equal to Nk. By increasing the number of factors and levels, the number of experimental runs grows hugely. For classical experiments, this brings high costs and time consumption. However, due to enormous diversity and combinations, the response quantity variance can be explained, decomposed, and attributed to all possible causes, thereby providing in that way an almost realistic depiction of the process. Besides FFD, there is a wide variety of factorial designs, and they differ in the insight they offer. Selecting the right design means identifying the best way to sample the domain of possibilities. Definitive screening design, DSD, unlike other screening designs, introduces the third middle level for continuous factors. At the same time, it lowers the number of required experimental runs to 2k plus 1, k number of factors, which can be very suitable when some process is affected by a large number of factors, 18. This design can estimate two-factor interactions using a low number of experimental runs, which is impossible in other screening methods. For the characterization of complex processes affected by a high number of factors and interactions, DSD could be a suitable choice for screening and even characterization. R.L. Placket and J.P. Burmann developed Placket-Burmann design, PBD, in 1946. Up to now, it represents one of the most applied screening methods for recognition of the most significant factors among a large number of variables. Classic PBD is a third-level resolution design that offers insight into only the main first-order effects. However, folding this design increases the number of experimental runs and resolution levels to fourth, thus enabling the determination of two-factor interactions. Taguchi design, TD. Despite its divided reception in the scientific community, Taguchi design, due to its practicality, became the most commonly applied experimental design, both in industry and science. Its strength lies in effective orthogonal matrices where factor levels are distributed in a balanced way, reducing the required number of experimental runs. Most orthogonal arrays are focused only on the main effects, but some designs allow the estimation of specific interactions. Given the practicality of TD, most of the experimental designs examined in this research are Taguchis. Some of the designs are suitable for screening, two-level TD, while others are more suitable for more in-depth characterization and optimization. Response surface methodology. Designs associated with response surface methodology, RSM. This class of designs was developed in 1951 by Box and Wilson. Over time, two main groups of designs have evolved: central-composite and Box-Behnken designs, CCD and BBD. They offer an understanding of the system behavior, reveal a type of connection between factor and response, and its optimization at the same time. CCD is usually applied after narrowing down important factors by some screening methods. It consists of central and axial points beside cube points, allowing insight into the curvature of response and estimation of higher-order effects. BBD is similar to CCD, but requires fewer experimental runs and does not contain points at the vertices of the cube, low/high points, which can be very useful for physical experimentation since extreme points are sometimes expensive or difficult to test. For this reason, compared to standard CCD, the BBD design contains regions of lower prediction quality. Statistical tools. In parallel to selecting representative runs that can sample the domain of exploration effectively, dedicated methods need to be employed to post-process the results of the experiment. In this way, qualitative and quantitative information on the impact of the different independent variables on the dependent variable is obtained. The analysis of variance, ANOVA, is an analytical and statistical procedure that determines if there are differences between group means in a sample and whether these differences exist only due to randomness or can be attributed to a specific cause. By comparing group means and variation among them, ANOVA decomposes the total variance and attributes it to all the different causes, thus quantifying the effects of various predictors, factors and interactions on the dependent variable. Design of experiments is a multi-purpose technique that can be applied in a variety of circumstances where a methodical examination of factor effects, and especially their interaction effects, is vital in order to shed light on complex aspects of a decision problem. Statistical design of experiments, DOE, is a powerful tool for optimizing processes, and it has been used in many stages of process development. Different designs of experiments, DOS, can lead to different characterizations of the same phenomenon, and how the optimal designs can be selected to obtain the best possible characterization of the process using the fewest possible experimental runs.